Today, I'm finally getting started on the real set of tests for my algae bloom experiment. And I'm bringing back something we haven't seen on this vlog in a while, the Pioreactor. Hey, I'm Elian, and I'm once again experimenting with microalgae. If you haven't seen any of these videos before, I'm developing a solution to algae blooms, a problem that affects millions of people around the world and causes at least $300 million in damages on the Great Lakes here in Canada. I'm working with a substance called modified clay, which is essentially like a powdery magnet that's really good at pulling algae out of water. And now I'm finally ready to start conducting the official tests on my algae using my modified clay. What I've done thus far is to add 10 milliliters of my culture of Microcystis aeruginosa, which is one of the major cyanobacteria that causes algae blooms on the Great Lakes, into this vial here. And you might recognize this vial because it's the vial from the Pioreactor, which I also have right here. A little out of frame because it's plugged into a cord all the way into the wall. But what this thing can do is, well, quite a lot of stuff, and I used to be using it for an experiment on algae growth a while ago. But now that experiment's done, but the Pioreactor still has use, specifically for its ability to measure optical density. Optical density is essentially a measure of how much light a substance absorbs. So this vial of algae absorbs a certain amount of light. And that's because it's all wrapped up in solution, the algae are just floating around. But when the algae get pulled to the bottom by the modified clay, the water is left clear and absorbs much less light. And we can monitor that using the Pioreactor. Up here is a graph of a test I did just a little bit earlier, and you can see first there's the algae, which is a just straight line at the bottom, then it shoots up when I add modified clay, and then over time it goes down and down as it removes both the modified clay and the algae out of solution. On a large scale, that's what it would look like to clean up an algae bloom. You'd start with an algae bloom on the surface of water, you add a bunch of modified clay, and it all gets pulled away. Then you can harvest that modified clay and mix it into concrete, which is the second portion of this experiment that I've been doing the last couple weeks. Now, the key thing that makes modified clay and not just regular clay is a substance called chitosan hydrochloride. It's essentially just chitosan powder mixed with some hydrochloric acid. But what it does is it makes the modified clay positively charged, which is what makes it really good at pulling out algae and gives it that magnet quality. So I'm running a series of tests, adding different amounts of chitosan hydrochloride to my clay to see which amount of chitosan hydrochloride results in the fastest absorption and the greatest absorption. All of which I can measure with that graph from the Pioreactor. So here I've got a beaker full of modified clay. I'm just going to stir it up as we're talking here. And what it contains is 1 gram of modified clay inside 100 milliliters of water, along with 2 milliliters of my chitosan hydrochloride solution, which is in this little bottle here. So I'm going to now add 1 milliliter of that to this Pioreactor vial. I'm going to let it sit for about 12 hours. So here we go. I have my modified clay over here and my solution of algae over here. And I'm going to get this dropper and add 1 milliliter of modified clay. Here we go. There. And I'm going to shake it up a little bit. And then I'm going to put the cap back on and transfer it over to the Pioreactor right here. Drop it in there. Oh, the cap fell off. Drop that in there. And it will now sit for the next 12 hours, and that modified clay will absorb all the algae, pull it to the bottom of the vial, and leave it completely clear, which we'll see on the graph, like I said, in 12 hours. All right, I'm back. It's been a little over 12 hours. I had to end up recording this in the morning because I didn't have time in the evening to record. But that hasn't affected the data that much, and the data is actually looking really good. Check out this graph. This is the graph of optical density over time, and it shows about the 22 hours that the modified clay and the algae were sitting there. And you can see it's got this pretty exponential trend, but let's talk about all the parts of this graph. Now, you're probably noticing the massive spike right at the beginning, but I want to talk about what happens a little bit before that, right over here. Even for like the little first hour, there's just this constant line. And what that is the original optical density of the algae solution, even before any modified clay was added. That was actually going while I was recording this video and talking about how this whole process was going to work. I was trying to, at the same time, measure the optical density of the non-modified clay algae. So we can figure out the baseline optical density and then see what the modified clay brings it down to by pulling algae out of solution. So that's a really great start. Now let's talk about that spike. That right there is when we added the modified clay. Modified clay has a much greater optical density than algae does because it's clay, it's gray, first of all, and its particles are much bigger, so it interferes with the light coming through quite a bit more. So the optical density shot up all the way above 500, up to 544, and then over time it started to drop off as the modified clay started to sink to the bottom along with the algae. Essentially, it pulled the algae down with it. So you can see this very quick drop off at the start, and then it starts to go down, and that's indicative of negative exponential decrease, which is really, really interesting. Now you can see by about 2 hours, it has gotten down to about 0.2 optical density, which is a pretty big decrease even from the 0.36 that we started with. And over time, it gets lower and lower and lower until after about 5.5 hours, it reaches below 0.01. That number is super important because that's the number that corresponds to the optical density of regular water, something I measured a little bit ago. So what that shows is that by 5.5 hours, the optical density of the water is just water. All the algae is gone, all the modified clay is gone. Essentially, the process is complete. Now, the other thing we care about is, well, how long it took to get there. That took 5.5 hours. And yesterday, when I did a test in the morning of chitosan and only adding 1 milliliter of chitosan to my modified clay, it took about 7 hours. So what we're actually seeing is that more chitosan makes the process go faster, which is super, super interesting. This is the data point that I really wanted to see. And now I'm excited to keep pushing it further. Depending on how much chitosan we add, could we get it down to 2 hours, 1 hour, maybe even 30 minutes? If we can add more chitosan and make the modified clay absorption process faster, that means that we can treat algae blooms faster and ultimately produce clay faster. That means we can avoid more and more damage to communities by these algae blooms growing uncontrolled. So there we go. I'm just running more of these experiments this week, and next week, I'll have results to show for all of it, along with all the concrete stuff that I'm doing in some of my other videos. So if you want to make sure that you catch this huge, big data analysis video that's coming out next week, make sure to subscribe on YouTube, follow on LinkedIn, and I'll definitely be seeing you in the next one.